9 a.m. in Houston Central Time, and welcome to this webinar. And thank you for finding some time to join today's discussion. And I think this is going to be super interesting training and discussion that you're going to learn a lot on the hazard associated with electrostatic discharge. My name is Emmanuel Adai, and I'm a senior process safety consultant from Sigma-HSE. So let me go a little bit about my personal background. And looking at my accent, I'm not from America, so I'm actually from Ghana, Africa. And with my background, I have a bachelor in chemical engineering. I have a master's in process safety engineering. Also have a PhD in process safety engineering, specializing on combustible dust hazard assessment, including electrostatic hazard assessment. I have over 40 publications on combustible dust and also 2 books, and also hold MBA in engineering management. Also hold a license in process safety and also general safety CSP, also licensing forensic investigation with regards to fire and explosion. I have a wide range of experience ranging from combustible dust hazard analysis, and also we have the Europe office in Manchester, UK. We serve all the European region. And also we have the Asia, India, which is, the office is New Delhi, which serve all the Asians. And also we have 2 ISO accredited laboratories. We have the one in UK, which serve the Europe and also serve the North America. So all our samples from United States actually go to our UK office, and the lab technicians and engineers are very, very knowledgeable. They know what they do, and they can actually understand your needs and perform the various tests to fit your needs. And we also have our Indian lab, which serve the Asia. So today's presentation will focus more on this, the hazard associated with electrostatics. And first of all, I would like to dive a little bit into the cause of fire, what are the conditions for explosion to actually occur. And then I'll also jump into the various approaches where you can actually assess electrostatics hazard. That will come from maybe how charge is being generated, how charge is being accumulated, because after generation, the charge needs to accumulate somewhere. And after accumulation, how does the charge actually dissipate or maybe discharge into the system, or a system which can create the hazard. And after discharge, we need to find a way where we can control this discharge so that it does not become a hazard. So this will be the outline of today's presentation. First of all, let's try to understand the fundamental of fire. In order for fire to happen, or any kind of combustion operation to happen, first of all, we need to understand maybe what is the fuel that I have. Let me use this typical example, and I love barbecue a lot, so I always use barbecue as an example. In case I want to do barbecue at my backyard, the first thing that needs to come to my mind here, somebody will say meat. Yes, if you have the meat, you don't have anything to burn it, that means you don't have a barbecue. So for a fire person, I'll think about the combustion operation first. So first of all, I need to know, do I have the fuel, which could be the propane gas? Do I have sufficient oxygen, that is oxygen in the air? Do I have ignition source? So in case I have my propane, which is connected to my maybe my burner, that's the first thing. And do I have oxygen to sustain it? And normally you have to create something to create a spark to ignite it. The same way when it comes to the industry. First of all, I need to have my fuel, which could be my acetone, my isopropylene, or maybe my ethanol, my methanol. These are the fuel that actually are handled in the various industry. Then I need to consider whether I have oxygen, because without oxygen, you cannot sustain this combustion operation. So I need to know whether I have oxygen to actually support this flame propagation. Then after having the oxygen, I need to also have ignition salt, something which is supposed to initiate the combustion operation. The ignition source could be electrostatic discharge. That is the topic for today. We could also consider hot surfaces, act from electrical equipment, maybe overheating of bearings. These are the various types of ignition source that needs to be considered. So knowing this fire triangle, we need to understand, okay, in case I have a solvent, how does this solvent actually ignite? There are some key parameters that we need to understand. First of all, we need to understand that this solvent, a pool of solvent, you apply heat or something like that, it's not just going to ignite. It needs to form a vapor at the surface of the solvent. And to have a vapor sufficient enough to sustain flame combustion is termed as a flash point. So we need to understand the flash point of this material. After knowing the flash point, we need to also know the concentration. I will dive into that very soon. We need to know the concentration, which is the lower and the upper flammability limit. We need to also know whether we have sufficient oxygen to sustain this combustion, and we need something initiator, which is all the ignition source. So that is for solvent. So as I mentioned, we need to know the flash point. You know, the flash point is the minimum temperature at which a volatile material will give off sufficient amount of vapor to form ignitable material. So having my pool of flammable liquid will not actually ignite unless I form a specific amount of concentration of vapor that can actually sustain this combustion operation. And if that vapor which is actually generated is able to burn at a specific temperature, it's termed as a fire point. Normally in the lab, we determine the flash point. After flash point, you are able to determine the fire point if the flame is able to stay on for some time. Then we know that, okay, at this point, a fire will actually occur. That is a fire point. And usually the fire point is always higher than the flash point. And you can see the table on my right. You can see we have some common material that we handle and the various flash point with either the open or the closed cap. And you can see acetone, which is very low. We can see taurine, we can see methanol, and so on. So every material that you handle, flammable liquid has a flash point. And this is very, very important to actually classify the material, whether it's a class 1A, B, or something like that. All of them depends on the flash point of the material. What about the flammability limit? Every material has a range in which this material ignites. If I have acetone, I have a range. So the lowest range at which flame can be sustained is called the lower flammability limit. And the upper, that is the highest concentration at which this material can actually sustain flame combustion, is also termed as the upper flammability limit. The range, the in between the lower and the upper, is termed as the flammability range. So this is something that we need to understand. Below the lower flammability limit, you are not going to get ignition. Above the upper flammability limit, you are not going to have ignition or combustion. In between them is where you can have ignition, and there are several parameters that can interfere with flammability range, such as the oxygen, addition of additive, and this is not the topic for today's discussion, but just for you to know. In between the flammable range, there's always a point where the flame is at a stoichiometric concentration, where we have an optimum, where we can have enough oxygen, enough fuel to ignite to release the most violent explosion. And so this is the flammability limit. So every material you handle at the facility, you need to the flammability limit to help you understand at what range should I stay, whether I need to stay for acetone, the concentration that you handle needs to always be low under 2.5 or above 12.8. So, but you don't want any concentration between 2.5 and 12.8. What about combustible dust? So we have handled the flammable, solvent, and gases. What about combustible dust? When it comes to combustible dust, the three main elements still hold. We need to have the fuel, we need to have ignition source, we need to have our oxygen. However, having the fuel alone, the oxygen and ignition source, we are not going to get a combustible dust explosion. So for example, in case I have a fuel that is a starch or maybe sugar, that's everybody handles sugar, I put it on the floor, I apply heat, automatically I'm going to get a combustion operation. So the flame will actually ignite or the material will ignite, but how far can this material ignite? That means it will ignite at the immediate area and it can easily be quenched. However, what about if I disperse the material? We know from basic chemistry, in case I disperse the material, I actually increase the surface area. And with the surface area increase, the reaction rate will actually increase. So the rationale behind combustion of solid, that is organic solids, I'm not talking about metal here. Metal goes under heterogeneous combustion and organic goes through homogeneous combustion. For organic solid, for example, if I disperse the material, the first particle will actually ignite. The ignition will actually give off energy. The energy release will move to the next one. Then the next one will also move to the next one. Then we have this homogeneous, the vapor or the energy that we release will actually create a vapor, and the vapor will react with oxygen to ignite. So homogeneous ignition, when dispersed in the air, act like a domino effect, where maybe first one ignite, move to the next, movement, then we have a combustion. So each of this energy which is released actually can accumulate. But if you don't have a term called confinement or enclosure, this energy release is just going to release to the atmosphere. So if I stay beside this combustion operation, the worst scenario is I'm just going to have maybe a burn, because the energy which is being released are actually disposed through the atmosphere. However, if I have a confinement, the energy which is being released is actually going to continue to accumulate, because there's no way to dissipate this energy. So it's just going to accumulate until a point where the energy release is higher than the material that is being used to handle the material, the combustion material. Then it's going to what? It's going to burst. That is explosion. So just to understand, fire is you have the fire triangle, you can burn the material. Flash fire is when you have the dust released in the air without any confinement. And if there's a confinement with enough energy, then you are going to get explosion. So just to understand this mechanism between the fire, flash fire, and explosion when it comes to combustible dust. So you need the confinement, you need ignition, so you need fuel and dispersion for a complete combustible dust explosion to actually occur. So there are several ignition sources that are actually applicable in industry. And most of you guys, I think everybody's in the industry, they understand this. You have open flame, which is something obvious and highly applicable. We have the use of cigarette, and somebody might think this is not common. How can somebody smoke in a flammable atmosphere area? And I did say to someone that I went to a facility where I saw somebody smoke a cigarette and just dump it on a metal pan, which is a bad practice. So I think I reported to the management, and they tried to enforce the system, because this could have actually caused any kind of fire or explosion hazard. And lightning strike, in case you handle any kind of material in maybe a silos or a bin or any storage tanks, you need to have a lighting protection. Cutting, welding, hot work permit according to NFPA 51. you have grinding impact, we have friction from bearings, hot surface from ovens and dryers. We also have self-heating or thermal instability or reactivity. For example, some materials can self-ignite without ignition source. In this case, as you have the power of the material, the energy generation is greater than the energy disposed. So in this case, you have heating of the system, which can actually self-ignite. A typical example is working on a wood yard or maybe a coal yard. Sometimes you can see a lot of smoke coming out. And this smoke, nobody actually ignited it, it self-decomposed by itself. You have electrostatics. I don't want to go more because that is our topic for today. We have spark from rated electrical equipment. And normally you need to, everywhere where you handle combustible or flammable material, you need to classify the material, the area according to NFPA 70 Article 500, or using NFPA 497 for flammable solvent and gases, or 499 for dust. And in this case, you need to ensure that every equipment which is actually located in the classified area conform with the various classification, whether it's a class 1, D1, or class 2 for dust. So this is something, a different topic altogether. I don't want to dive more into that. We also have electromagnetic radiation and stray current, which is actually not common in industry. So these are the various applicable standards that we normally use. We have in the United States, we have the NFPA 77 that recommended practice for static electricity. So the 77 is always used. In the Europe, we use the IEC or TS 679 and the section 32-1. So that is something which is used in the European standard. So now we jump into the electrostatics itself. You know, we actually encounter some kind of static electricity in our home. Sometimes we don't actually realize it. A typical example is sometimes when you try to press on the knob for elevator, sometimes you get a shock, right? Or sometimes when you try to remove a coverall in the lab, you try to remove some shirt or maybe some jacket, sometimes you hear some cricket sound, or sometimes you can get a shock. These are all a typical example of static electricity. And before we dive into them, I would like us to understand some key terminologies, and this terminology will follow us throughout this presentation. So it's actually good to understand them. The first one is conductive material. What is a conductive material? A typical example is metal. So a typical example is metal. Conductive material is the type of material which is not able to actually retain charge when grounded. So the term here is not able to retain charge when grounded. So if it is not grounded, and we'll go into the grounding and bonding very soon, if not grounded, it's not connected to the earth, that means the charge accumulation will still stay there. But as soon as you connect it to the earth or grounding, then the electric potential will actually be zero. It will dissipate all the charges. That is a conductive material. The second one here is static dissipative material. That is a semiconductor. That's what we say. So this kind of material is also kind of a conductive material. It can accumulate charges, but it will be able to release charges. So the rate of charge release or dissipate is higher than the charge accumulation. It's not like conductive where it will go to zero, but this time it will actually dissipate all the charges at a specific rate. And maybe sometimes you can have some residual charge accumulation, but that charge accumulation is not significant enough to actually cause any kind of hazard to the facility. The next one is non-conductive or insulating. That is normal plastic. So these materials actually allow charges to accumulate. It does not have a means of dissipating charges. So if I have a plastic and I have material accumulation there or charge accumulation there, it will continue to stay there, stay there, stay there. So that's why we always will recommend in the industry where you handle any flammable materials. Always you need to use conductive or static dissipative material for handling this material, so that whenever charge accumulation can actually dissipate. So for non-conductive, even if you ground it, it will still, because it does nothing flows through it. So whatever charge stays there will continue to stay there. and we will dive more into that very soon. Also, we need to also understand another term, electrostatic discharge. Discharge means the transfer of charges. So it's the phenomenon whereby charge equalization occurs between two objects at different electrostatic potential. That is between an electrically charged object and ground object. A typical example here is I have one metal A, and I have another metal B. Both of them has different electrostatic potential. So I can actually connect a bonding string. Then the charge will be transferred from one A to B, which is a discharge operation. And if also I connect a grounding cable, that's an A to A, then it will transfer from the charge will transfer, or the charge accumulation on the conductive or the metal will transfer to the ground. That is what a discharge, to ensure that I have equalization of electrostatic potential. So that is what electrostatic discharge. And we have various forms of discharge, which I don't want to dive right now more into that. We have a spark from maybe metals, we have a blast discharge, we have cone, we have coronal discharge, and we will dive into that one very soon. The main focus here for you to understand the mechanics and these terminology so that you'll not be confused when moving into the next stages. The next aspect here is bonding and grounding. Bonding is electrically connecting adjacent conductive object together to prevent voltage difference. And I just mentioned it. In case I have A and B, and each one of them has an electrical voltage difference. In this case, if I connect something, or maybe a conductor from A to B, so that I can have a charge transfer as bonding. And for grounding is if I connect that equipment to the earth or to the ground so that it will dissipate all to the ground, then I have grounding, or something in Europe we call it earthing. So how do I actually assess electrostatic hazard? The first thing that will come to my mind here is I need to understand, how does this charge actually generate? How does it accumulate? How do I actually dissipate or discharge it? And what are the key parameters that I need to know when I have this discharge? And what are the energy that can actually ignite this material that I handle? So generation of charge comes in different forms. The first one is contact. In case I have very sensitive material or highly charged material, then I touch it, automatically I will have transfer of charge to myself. The second one is induction. Induction is just a process of generating electrical current in a conductor by placing the conductor in a changing magnetic field. That is, I'm trying to induce. So I have a magnetic field, then I place a material there. So I try to induce the material to generate a charge or to accumulate a charge. That is for induction. Then also have another way of where I can generate a charge, which is a coronal discharge. And coronal discharge always happen in a fluid-like medium, and it's what a discharge occurs when a direct or indirect or alternate, indirect is alternate, current is created between two electrodes brought to a high potential and is separated by a neutral like air, such as air. So this happens somebody say in a vacuum, in air. So I have two, whether alternate or maybe a direct current with two electrodes. Then I actually brings these electrodes together and is separated by air. Then this environment, the air will actually generate some kind of charges. So after knowing this charge generation, how do I actually accumulate it? So accumulation will actually happens on first isolated conductor. If I have a metal and it's not grounded, and whatever charge which is accumulated will stay there. Or insulating objects such as plastic, when maybe a plastic is actually accumulate charges and the charge will also stay there. We have personnel. Human body generally is a conductor of electricity. And if the human body is actually isolated, that means whatever charge that is being generated to or accumulated in the body will actually continue to stay there. We also have powder. Normal powder that we handle can also accumulate charges. We also have liquid material, so can also accumulate, and we'll dive more into that very soon. So after accumulation, how do we discharge these accumulated charges? So it can come in the form of, number one, a spark. It could come as a blast discharge. It could come as a spark from conductive object like a metal object, where, and a typical example is sometimes you have a battery, you try to connect to the other terminal, you can see sometimes a spark, different electric potential happening, and you can see that you get a spark. A blast discharge is where you have a conductor insulative material. And a typical example is normally, in case you have a balloon. When I was young, normally you have a balloon, you rub it on our head, and you can see that after that it will stick. That is what we actually, the charge from us are being discharged into the insulator, which is a balloon. We also have a propagation blast discharge where we have a metal, then we have a thin layer, such as a paint, where the paint will serve as a capacitor, and I will dig more into that very soon. We also have a cone discharge where, in case we have maybe a silo, where we actually fill the silo, and with this silo, depending on the volume resistivity of the material, it is able to retain these charges. And we have the corona that we have already discussed. And there are key parameters that we need to also understand. The first parameter here is the ignition energy. So everything about electrostatics comes to ignition energy. The ignition energy is the minimum amount of electrostatic discharge that can actually ignite a material. So every material has its own ignition energy. So below that energy, this material, the material is not able to ignite. So if the minimum ignition energy of maybe a starch is 30 or kilojoules, if maybe I have a starch cloud and the energy is 20, automatically it's not going to ignite. So that's something that we need to understand. And ignition or fire or ignition actually occurs when maybe the ignition energy or the discharge is actually greater than the minimum ignition energy. And every material you handle, you need to know it. And our lab is capable of determining the minimum ignition energy for almost every material which is being handled on Earth. So practically, how does this charge, electrostatic charge, generate? The first one is personal. As I mentioned, human body is a conductor. Sometimes working on insulated flooring, if the floor is actually insulated and has charge accumulation, that charge could transfer to the individual. We also sometimes removing the wall, also this charge accumulate. Actually, you can hear, as I said, sometimes you hear that noise, cricket sound. And also for powder, we have sieving operation, we have pouring of powder, we can generate electrostatic discharge. We have auger or skill conveying. During the skill conveying, this material kind of collide with each other, and we could generate our electrostatic discharge. Grinding operation also created, and micronizing. Pneumatic conveying is very, very common, because during pneumatic conveying, either it's positive or negative conveying system, this material kind of collide and cause attrition, and this collision and attrition can also generate charges. I also have liquid transfer in hose or pipe. Mixing or agitation can also create a kind of spark like discharge, and also we have filtration. And sometimes, in case we have a movable cut on insulated or rubber and insulated floor, and we can also generate electrostatic charges. So as I mentioned, we have the various discharges. So the generation, we have the discharges. Discharge here is the spark. Discharge actually depends on the resistivity of the material, how the material can resist the current flow or discharge flow, and the geometry of the object, and also discharge initiation electrode. So the first one is spark discharge. This is a discharge between electrostatically charged conductor. As I mentioned, if you have a metal to a metal, or metal which is actually has accumulated charges to a ground, this is what a spark type. So if we have a kind of energy release through this kind of connection with a conductor or a metal, to maybe a different kind of metal component. As I use the battle, for example, you have a spark ignition. And usually you can calculate the store energy using the half capacitor times voltage square. And in this case, you will be able to know the capacitor of which the amount of energy which is being stored, whether in picofarad or microfarad. And you also know the voltage. And in this case, you'll be able to calculate the stored energy. And spark type ignition source usually can generate an energy up to 1,000 millijoules. That is one can ignite gas, solvent, and dust, because this energy is very, and you don't want this in the industry because it can ignite almost every material that we handle at our various facility. We also have a blast discharge between insulator and ground, and I think I have already discussed this. And this discharge can generate an energy up to 4 millijoules. And based on research, this can only ignite gases and solvents. And they try to use this discharge to ignite dust. It couldn't. So if you are handling combustible dust, you should not worry about this kind of blast discharge. What about propagation blast discharge? This is the most serious one. Discharge on the surface of a charge insulated backed by a conductor, or you have a surface coated with a thin layer of insulating material which will act as a capacitor. For example, in case I have my silo or maybe my static dissipative material such as a bin or maybe a unique container, then I coat this container with maybe insulative paint. This paint will actually serve as a capacitor because it's an insulative and the metal is there. So the discharge between them will serve as a propagation blast discharge. Or in case I have a flexible hose, with the flexible hose, we have those spiral wires inside. And that wire is a metal. We ground it from the end to the end, and we have the insulator. So in case there's a breakthrough voltage, then automatically I'm also going to have a propagation blast discharge. Or in case I have my plastic liner, sometimes I have maybe my container, metal container, which is more either bonded or grounded, then I have a plastic liner, and this can also create a propagation blast discharge. This can actually generate an energy between 1,000 millijoules to 2,000 millijoules, and this can actually ignite almost every material. So that is something that we need to also understand. We also have the blast, the bulk or cone discharge, and I think I'll dive more into that one very soon too. It occurs when filling a container. When filling a container from the top, as it drops into maybe a silo, and you see that it forms kind of a cone, and if the material is super insulative, depending on the volume resistivity or the surface resistivity of the material, then it will actually accumulate those charges. Sometimes you can see some kind of a light, luminous light inside the container in the form of a cone or a cone shape. And this can actually generate an energy up to 25 millijoules, and it can ignite gas and vapor. And usually it depends on the particle size, because bigger particle size will have more drop-in velocity, which will create more charges. So there are key parameters. In case you tell me, okay, Dr. Ade, come to my facility and do electrostatic hazard assessment on my operation, I need to know some key parameters. That's where I'll come with maybe my mega ohmmeter, my field meter, which is JC 140. So I'll come with all my various equipment to your facility. First of all, I need to know the minimum ignition energy of the material. That can be done in the lab. So to know the minimum ignition energy, I'll be able to know, okay, is this energy that you are going to release through your operation, is it able to ignite the material or not? Then I want to know the resistance to the ground, whether maybe how many ohms. And that is that's something that I need to know with my mega ohmmeter. I need to know maybe in case of operators, what is the resistance to the ground of operator, the footwear, maybe the gloves that they use, what is the resistance, is it static dissipative, is it conductive? I need to do all these kind of measurement. I need to know the volume resistivity of my powders, whether maybe it is more than 10 exponent 11 or 10 exponent 9. If it is less than 9, we consider it as static dissipative. If it's more than, we consider as insulative. I need to know, in case I have a hose, if liquid, I need to know the liquid conductivity, which can be done in the lab. I need to also know the surface resistivity of the material that you are using, whether it's a container, you need to know the surface resistivity, whether maybe it's static dissipative or maybe static dissipative or maybe insulative. And I need to also know chargeability in case the material travel in a hose or in a pipeline, the material collide with each other and start to charge. So I need to know this chargeability. So these are some of the key parameters that in case I want to perform electrostatic hazard assessment, I need to know all these to actually assess the risk associated with your operation. So knowing those terminology, knowing those parameters, knowing those hazards. So the hazards are despite discharge, those discharges. How do I actually control this electrostatic discharge? That is the prevention part of it. So now we learn something about how do I actually generate discharges? How do I actually accumulate discharges? How do I actually discharge it? What are the key parameters? Then the next question is, okay, Emmanuel, you have spoken enough. How do I actually control it? How do I ensure that my plant is safe? And that's where we are going to jump into it. The first one is controlling electrostatic hazard, that is for metal equipment, as I said, for metal. So accumulating of static discharge can be prevented by grounding a conductor. And we already understand grounding. Grounding is connecting the equipment to the air, to the ground. That is the first thing. So grounding is a process of bonding one or more conductive equipment to the ground so that all objects are at zero electrical potential. That is also referred as earthing. So at each plant, they have an air to the ground where everything goes and connect to it. So that is earthing. So usually a resistance of 10 exponent 6, less than 10 exponent is generally adequate. And in case it's a metal to metal which connects to the ground, you always want to stay below 10 ohms. So, and that is something that maybe I can do at your facility to ensure that if it is more than 10 or between 10 to 25, it's okay. But in case it go beyond that, that is a conductive equipment to the ground, then there will be a question mark that we need to answer, whether maybe your actual grounding is okay or not. And sometimes we have to use, you can see the picture, we can use the multi-threaded copper, as you can see, or we can use a stainless steel. And effective bonding and grounding requires, number one, identifying the conductive equipment or object within the process. Every conductive equipment needs to be identified. Then we have to do effective bonding and grounding. We need to ensure that each equipment is grounded. Grounding is connecting to the earth. And also periodic inspection to ensure that all bonding and grounding are actually effective and you don't have a break. And this is something that I see a lot, and I've been to industry where operators goes to equipment, does a kind of a maintenance, and they remove the grounding strip, and after that they forget it. And also investigate an incident where there was a fire incident where the person filling a tank, the person forgot to reconnect the grounding cable. So that is something that needs to be addressed in the industry, and this is the killer side of everything, where maybe forgetting or not inspecting, ensuring that everything is actually intact before starting any kind of operation. And in various rooms, and normally in case I come to a facility, most of the facility, they have, we call this one, the picture on the left, as sort of a bus bar, bonding or grounding bus bar. So with this bus bar, you have, can you see the line on the top there? And that is what a grounding cable, which is connected to the ground. Then you have this bus bar, which you are going to connect all your equipment with. So this is supposed to be a zero potential. Then electrical potential from here to here, or maximum of 10 ohms. So everything here is actually grounded. So you connect your various equipment to this bus bar, and equipment will automatically be bonded and grounded. So that is something that facilities can do. Or you can connect on the far right, the equipment to the ground itself to ensure that the equipment is grounded. So in each room, each operation is always advisable to have this bus bar there. Then in this case, you connect the bus bar to the ground. Then each equipment, you can see you have multiple connections where you can connect this to ensure that all your equipment, your bonding string, your barrel, or any kind of conductive equipment are actually bonded and grounded. Excuse me. What about controlling metal containers? Metal containers, and that is the example I gave. Sometimes you could have this insulative coating. Sometimes you could have some kind of corrosion. Sometimes you can have some kind of material buildup. So ensure that grounding at all times during filling and emptying. And that is the problem I had with the incident investigation that I did. They forgot to connect it. And applying ground clamp to commencement of filling. So this is the grounding clamp, and the grounding clamp actually use a hardened steel point, as you can see in the middle, the top one, the hardened steel point, which will actually penetrate through maybe through the corrosion, through the paint, to ensure it actually touches the metal. So that is something that needs to be addressed. Anytime you are handling any kind of flammable solvent, you need to ensure that they are properly grounded. And sometimes we might assume connecting to the clamp automatically is ground enough. Sometimes you need to ensure the metal to metal touches it to ensure complete. And actually, you can also do use mega ohmmeter to check the resistance, whether actually the material is actually bonded or grounded. The next aspect here is personnel. And sometimes when I see people say, "Oh, really? Can I actually serve as a source of ignition and cause fire?" Yes, because human body is a conductor. And we can actually accumulate static discharge if we are isolated from the ground. So normally when I go to every facility, my shoe is always static dissipative. And a person insulated from the ground can actually accumulate a significant charge by actually walking on insulating surfaces or manually pouring or powder or liquid into maybe a container. And that is normally the very, very common in industry, maybe powder in the pharmaceutical, in the ink industry, which where they handle both flammable solvent or maybe powder. And in this case, handling mixture could be formed inside the container. However, during damping and you are not grounded, the charge are being generated. And if the ignition energy is less than 30 millijoules, automatically you can be engulfed in the flammable atmosphere because you are damping under abnormal situation. Maybe a cloud is going to form around you, whether vapor or gas or dust. And if you're not grounded, you can discharge enough energy that could actually ignite this material. A typical another example is when you are having tag A, B, and D, not C. C, I'll come to C very soon. So A is insulative and material which does not have any kind of way to dissipate charges. And we have B and D. I'll come to that. I don't want to drink the soup whilst my food is still not ready, so I have to wait until we get to that particular session. And sometimes blushing against an object, as I said, in case you have a balloon, you blush it, you can see that it will automatically charge. Or maybe in case you have a plastic container, you blush it, you can see that this material will actually automatically charge. During normal activity, the voltage on human body typically can go up to 10 to 15 kilovolt, and as little as 200 picofarad capacitor, the energy can be reached up to maybe 10 to 30 millijoules, which can actually ignite dust, gas, and solvent. And this has actually caused several fire and explosion incidents in the industry. So how do we actually ensure that the operators are actually bonded and grounded? The first one is using footwear. So you can see this one. Normally, most of them has a yellow tag. You can see the picture, the middle picture on the right, and normally it's indicate ESD. So anytime you are working in a flammable atmosphere area or where flammable atmosphere, we need to ensure that you have static dissipated shoe. Having the static dissipated shoe actually is not enough. You need to ensure that the flooring where you stand is also conductive. Normal cementing is conductive, or you can paint it with a static dissipated material, or you can have static dissipated mat For ergonomic purposes, excellent. If I'm a worker who stands at one place, I'll tell you I need static dissipative mat, which has a cushion and ergonomically it's really, really good. Or you can have a grounding wrist strap, so where you can tie it to your wrist. But that one, the disadvantage is in case you move more often, that means you cannot use this. And always you need to ensure you measure. Sometimes we might think that we have static dissipative shoe, but actually this bottom is really, really dead. And in this case, we will not be able to get proper grounding. That's why always we recommend that you have something to test it always, to ensure that actually we make between 10 exponent 6 to 10 exponent 8 ohms. And sometimes some people, they have actually programmed it where as soon as you attach to yourself, it will turn green or red. That is very, very important. Sometimes we can use a shoe cover or gloves, which is very, very important. If it's a shoe cover, you can see you have the static dissipative strap in the middle where it will actually touch to the ground, and the ground needs to be static dissipative conductive, or it needs to be bonded and grounded. Sometimes we could also use a gloves, which is also used when we are trying to transfer porous materials. What about insulative materials? So insulative materials are also something that we need to actually address because it actually accumulates various charges and it does not dissipate. So a typical example is what you see here. So in this case, when you are handling any, you handle material in any flammable atmosphere, you need to ensure that these materials are not used. You need to have actually static dissipative or conductive material which actually you can bond and ground and dissipate the various charging. And usually we need to know the resistivity, the surface resistivity always needs to stay below 10 exponent 11. And this we can determine in allow. So we need to ensure that every equipment that we use at flammable atmosphere area are either conductive or static dissipative. And also, how do you also control linings? You know, plastic lines. Sometimes we have these linings in the powder industry, in the industry, and you have this metal container, and you have sometimes be a fiber drum. If you are handling flammable material, this material needs to be static dissipative. For example, in case you are handling a material in non-flammable atmosphere, such as solvent, then you can do a breakdown voltage where you can use a field meter to determine the breakdown voltage. And if it is below 4 kilovolt, then it's sufficient. But always you need to ensure that these materials are actually static dissipative and it must be bonded and grounded. And this is a typical example of it here. When I said propagating blood discharge and blood discharge. And these key parameters are very, very important. For example, you can see this flexible hose here. You have this metal spiral wires inside. And if the hose is conductive and you have the metal inside are bonded and grounded, you're okay. However, if the metals are actually bonded and grounded, yes, then you can do away with spark type ignition source and you can do a blast discharge. However, you still have propagation blast discharge where you can see the picture on the right, the top right. You can see there's a breakdown voltage between the metal and the insulator, which is the plastic. So anytime you're using this kind of flexible hose, you need to ensure that the hoses are actually static dissipative or conductive hoses and the wires needs to be bonded at each end. So how about controlling electrostatic hazard for liquid? So electrostatic charge generation can arise in various liquid handling operations, such as when you are filling, sampling, filtration, and mixing. That is something very, very common in the industry. And depending on the conductivity of the materials, it can create significant amount of charge that could actually discharge. So normally, if you have low conductive liquid or maybe liquid in insulated container or vessel, even though the liquid could be conductive, but the liquid is stored or being transferred into insulated container, that means it's still the same boat. Or liquid mist normally is having its thing is droplet. So whether it's conductive or not conductive, it's still a hazard. And these are some of the conductivity of this material. You know, acetone highly conductive, and when you come to gasoline, you can see low conductivity. And these are, so always you need to know the conductivity of your material. Knowing the conductivity will actually help you to know, okay, is this material insulated? Do I need to add static or anti-static material into my liquid to actually increase the conductivity? So how do we actually control this hazard associated with liquid? The first one is use electrically grounded metal equipment. That is very, very important. So as I said, if you're using a drum, this is electrical metal equipment which needs to be bonded and grounded. So all plant items such as pipe, vessel, container should be electrically grounded, or we need to use static dissipative material so that every charge accumulation could be discharged or dissipated to the ground. Second is we need to increase the liquid conductivity. So if, for example, you have this liquid here, if it is low liquid conductivity, you can add anti-static additive to increase the conductivity of the liquid. And this could be done in part per million. That is just a droplet, because adding more is actually going to influence the material, the productivity or the quality of the material. A typical example here is when you have a filter or a valve. So when you have a filter located in a high charge generation item such as pump, and this could actually also generate those charges, and you can control liquid entry. Sometimes in case you are failing, you don't need to just draw from the top to the down, otherwise going to generate or going to splash on the bottom, which is going to generate charges. Or on also in the process of filling, it's always better if you can drop it to the down so that it will not going to have any kind of splash, and this can control static discharge during filling or emptying of any liquid material. What about powder? So during the transfer of powder, static electricity are being generated, and which depends on maybe the particle size. I mentioned initially we have something called cone discharge or bulk discharge, where you have maybe a silo where you drop the material by gravity or by pneumatic conveying system. Depending on the volume resistivity of the material, whether this material can actually retain charges or maybe it can dissipate charges. If it can retain charges for a long time, you can see the picture from the bottom. When filling, you can see this kind of the dots kind of a growing or luminous charges which will form on the surface in the form of a cone. And this can generate an energy up to 25 millijoules, and it can ignite gases, that's and solvent. So normally we always have ionizing thread or something ionizing which will stay in between the middle of the container, which will actually dissipate these charges into the ground. So which is very, very important, and it all depends on the particle size of the material. Higher particle size, high energy generation or high charge generation. And in case maybe you don't have any flammable atmosphere, maybe dropping it by gravity is actually not going to create a lot of charges. The last aspect is handling flexible intermediate bulk container, and this is something common. I see it almost everywhere, in the pharmaceutical, in the food industry, almost every industry that handle combustible powder. I see this kind of super sacks there. And there are 4 main types of super sacks. We have the type A, we have the type B, we have type C, and type D. What are the differences between them? Type A is no use area when the material is explosible. That's all that I was saying. If the material is flammable, you should never use a type A. And you can only use it if the minimum ignition energy of the material is actually greater than 1000. So it's actually constructed from insulated fabric or plastic sheet with no provision of controlling any type of static discharge. It has no provision to control static discharge. And normally you can use it for only materials with higher ignition energy. What about type B? Type B is also constructed with insulated plastic or fabric sheet design, and this has some kind of ways to prevent spark discharge and also propagation blast discharge. However, this also has some kind of limitations. If the ignition energy of the material is less than 3, then don't use the type B because it has this limitation. And it should never be used in flammable atmosphere such as solvent or gas, where in areas where you handle flammable solvent or gas, this should never be used. The type B is always, somebody will say, it's cheap and it's good. However, there's a really trick, and I think last week I visited a facility. They were using Type C. I was happy. I clapped for them. But getting close to the equipment, I noticed that they missed the point. Type Type C is actually constructed from a fully interconnected conductive thread. So as you can see, the bottom for the picture from the bottom, you can see this black thing there. That's the conductive thread, and this needs to actually be this actually needs to be bonded and grounded. So you could have the Type C, everything will be okay, but if you don't ground it, you are missing the point there. And also it can be used in the solvent, gas, and dust atmosphere. The Type D is always the best option to go, but it's super expensive, which is concerned with a special static protective thread property, and you can control any kind of, it can break any voltage. You can use it under material with less energy, solvent, atmosphere area, and gases. So these are just a table for you to. So we have the type for non-flammable atmosphere, can use any one of them, but depend on the ignition energy, greater than 1,000, you can use all of them. Between 1,000 and 3, you can use B, C, and D, and less than 3, you need to use C and D. And also we have the atmospheric, that is the classifying area. So if you have for combustible dust, you have to use A, B, C, depending on the ignition energy. But if you have combustible gas atmosphere, such as solvent class 1 area, division 1 or 2, then we have to use C and D. So I think that brings to the end of today's webinar, and thank you very much for your time, and I hope you enjoy it. In case you have any question, I'm available. I think I did well. I'm able to save 4 minutes for questions, so you can type your questions. I'll be more than happy to actually answer any question that you have, or you can contact me direct, and you can contact us in case you need any static or you have any static electricity problem at your facility. Just reach out to us and we'll be more than happy. We can come there with a lot of our tools, our equipment, to ensure that your equipment or operations actually actually bonded. And okay, so so I have a question. Vulnerability tells us about chargeability of powder. The vulnerability actually indicates whether the material is able to retain charges or not. So some materials are insulative. So if you have any charge accumulation, is going to actually stay there for a long time. And some materials are also conductive. For example, in case I have a normal material, what kind of normal just starch or some materials, these materials are highly insulative. And the chargeability, in the other hand, tells us once I'm transferring the material, is the material able to accumulate discharge during the transfer of it. So it's a different thing altogether. So the vulnerability actually tells us, okay, if I have this kind of material there, is it able to retain charges for a long time, or is it going to actually dissipate charges? And normally we also determine the charge realization time, where we need to know what is the minimum time that is required for the material to completely discharge. So these are the difference between them. So chargeability is when moving the material, during conveying the material, is the material able to actually get charged during the transfer operation? And the vulnerability is when the material is there, is it able to accumulate charges? So that is the question there. Large particle equates to higher charging generation, yes, which is yes. So in case you have large particle, when filling in a container, if the particle size are big, dropping it hit each other, we have a larger collision and it's able to generate large charges. We said, what is the difference according to you between grounding and bonding? Bonding is you have two metal equipment. You connect from one equipment to the other, which is bonding. And connecting those equipment to the ground, to the earth, is called grounding. So those are the two different between bonding and grounding. I can have equipment which is connected to the ground, but if I have another adjacent equipment which is not directly connected to the ground, then I have maybe a metal wire or conductor equipment to bridge that gap, the same electric potential. That is what grounding. Clarify the type of safety shoe that should be worn, assuming the floor is conductive. Normally, you have ESD shoes, which is super common in the market. So if you are looking for any, you go to Amazon, you type ESD shoes, and normally you need to test it. Normally, in case you where you use ESD shoes, you need to have something to test it. But this is super common in the industry that you can actually use in the market. Okay, so I think yes, I think I answered the questions, but I think you have my phone number. It'll be there, our email, and thank you very much and for your time, and you can just contact me anytime. Thank you, and thank you very much, and I'll be expecting to receiving various emails and calls from you guys so that I can help your facility. Thank you very much for your time.